Here we go. All right. So, big difference. How fast you dissolve something versus how much you can dissolve. Huge difference, okay? Let's think of ways we can do both. You can raise your hand or shout them out.
Stir.
Go ahead.
Stir.
Which one?
The radio.
Good. So, examples here, right? Examples would be stirring. Oops. Sometimes I have mild cases of dyslexia. Stirring. I do. I think it's good writing on the board for all these years. I sometimes get the letters screwed up. Stirring. What else? Shaking. Shake and bake? Possibly. Yeah.
Heating people.
Ah, yes. Heating. Examples over here. Sorry, I don't know where my M went. Examples here. Heating. Heating the solvent. You saw that making the rock candy. That's very obvious. Okay. If you were to leave the hot plates off, the 400 grams would never dissolve. Not all. Okay. So you heat it up, you can dissolve more. All right. What else? What's this really doing? What are you doing there? You're breaking the solute into smaller pieces. So you're making smaller pieces, and what that really does is it increases what? Surface area. Very good. Increases surface area. Increases surface area. Imagine all of you stood up and just clumped in the middle. Who do you want to be right in the middle?
Tyler Boyd.
Tyler. Tyler's right in the middle. Okay? Tyler's right in the middle. Well, maybe I have an unlimited supply of water balloons, and I start throwing them at you guys. Tyler's probably not going to get wet. Why? He's in the middle. He's protected by all you guys on the outside, right? So the analogy there is if you put a clump of sugar, clump of salt, whatever, anything that dissolves in water, so a big chunk of it, the middle of that chunk is not being touched by the water. It's going to take a long time to eat away at the outside to get to the middle. So when you shake or stir or mix it up, you're getting all of the clump there broken up. So that's like if you guys are in a clump and you just disperse, now Tyler's vulnerable and I'm going to hit him right in the face. All right? Water balloon. Pow. For not handing in your lab. So that is what that means, okay? Increased surface area. So all of the solutes is exposed to be dissolved. So the next unit, that's also a key. If you want something to react better, how do you start a fire? Like a bonfire or a fire, a campfire, how do you start it? You can't take a giant log and just hold a flame to it. It's not going to work. You use paper. What else?
Twigs.
Twigs. Twigs are smaller pieces, higher surface area, mixes with the oxygen, easier to create a fire, okay? Then you can put the big pieces on once you get the smaller pieces going. So that concept applies to lots of things. All right, what else? Anything else we can do here? I said in lab. Well, there's one more here. Decrease pressure. Increase pressure. All right, let's do it this way. Let's put a little star. We can increase pressure if it's gases, right? Parenthesis for gases. So yeah, if you increase pressure, gases will dissolve faster. And actually over here, same thing. Increase pressure. All right, put a little star. It'll also mean you can dissolve more gas as well. So, but pressure only really affects gases, not really so much solids or liquids. Okay. Those are the biggest, that's it. Those three really. You can add more water. Hannah said that this morning. I think someone said it yesterday in 8th. But you can add more water, but it isn't as dramatic of an effect. So if you want to add it, you can. But if you really want to stir up, speed up how fast something dissolves, these three, by far. Okay. And then if you want to add more, this is kind of the only option. You can also change the pressure. That might work a little bit for solids and liquids. That's why number 8 on the lab is kind of challenging. Because what's the other way to make it super saturated? You can change pressure. Period 6. You guys just got lucky. Actually, it's just you two, right? Yeah. Okay. anyways, so that's it basically for increasing solubility. Pressure changes for gases, heating, and then obviously the opposite, right? The opposite is true. So if you don't want to dissolve it fast, don't stir it, cool it down, and then you won't dissolve as much unless you're gases, right? So that's actually another thing we should add here. We could heat the solvent, or we want to cool the solvent if it's gases, right? We learned that yesterday. You want it to be colder. So if you keep it colder, more gases can dissolve. That's increasing solubility. So it does depend on what you're talking about with gases or solids or liquids. But I don't think I do a good enough job spelling this out, so I'm really trying to right now. This means you can add more to the same amount of water. This means you're not adding more, just dissolves faster. So eventually, this here, you'll stir it, and eventually if you keep adding solute, it won't dissolve. It'll just spin around. You're going to have to heat it, all right, to get it to dissolve more of the solvent. So solute. Big difference there. Questions? No questions. All right. You basically knew this already just from living life. You just have to think about it and apply it. The other gas stuff we just talked about. All right. So we're done with that. All right, dilutions. Okay, what is a dilution? Matt Penny.
That is a good question.
All right. All right, I'm just going to get right to it here. M1V1 equals M2V2. Write that down. This is an equation. It's on the back of your reference tables. It's how we figure out how to make dilution. So I'm going to make one here. All right, so I have potassium permanganate solution. It's probably permanently staining my, what's this called?
Something flask.
Erlenmeyer flask, right. So this is very concentrated. How do we know? It's very dark, right? Concentrated. This would be dilute compared to this. So how would I dilute this? Add water, right? Good. Well, that's easy to understand, I think, right? I know a lot of people who don't like orange juice just straight up out of the container. It's too sweet, so they pour water in to dilute it a little bit. You know anyone who does that?
I do it.
Almost everybody I know does that.
Orange juice.
People who I know who drink orange juice, they do that. They add orange juice and a little bit of water because it is very sweet. Anyways, now let's say, stay with me, let's say this is called a stock solution. What is a stock solution? It's a solution you get from your stock room. What is a stock room? That's the back room where you keep all the chemicals. That's what it's called. So you take a stock solution. Let's say the molarity is 12. Let's write this down. So let's say we have a 12 molar KMNO4 solution. That's what we have right there. And we have, we'll just say 75, we have 75 milliliters. Okay, right in that flask. Now, I want to, okay, or we want to make a .5 molar, 0.5 molar solution with a volume of 250 milliliters. So we're starting with 12 molar KMNO4. We want to make, oh, I'm sorry, I should have wrote KMNO4 again. We want to make 0.5. So we're going from 12 to 0.5. It's weaker, lower molarity, dilution. We're adding a bunch of water. But we want a specific volume of 250. This is called a volumetric flask. These are nice. I don't need to mess around with graduated cylinders. You guys probably can't all see it, maybe up front. There's a line right here. That line is exactly 250 milliliters. So all I need to know is a ratio of molarity to volume. So I know the molarity here. I know my volume is 75. That's how much I have, but I don't need all of it. I'm not going to take all of this and pour it in here. I'm going to take a little bit of this, just a little bit, put it in here, then take distilled water and fill it up to the line. I put the cap on, I shake it a couple times. Now I have the 0.5 molar solution. That's literally how I would make a solution that if you guys are using in lab, and I don't want you using a really concentrated one, I would use this equation, I would do some math, and then I would actually go make it. So I'm going to do that with you right now, explain how to do it, and then we'll go back and I'll show you how to do it, just so you can see it. It's nothing, you know, super spectacular. It's just literally adding two things and then that's it. You're done. But just to see what this word means and kind of how you do it. So I'm going to give you some help, and I'm going to have you use this equation right now. 12 molar is going to be my M1. 0.5 molar is going to be my M2. That's my desired solution. That's the one I want. I have 12. I want 0.5. My V2 is going to be 250. That's my final. So look at this as 1 and 2 as initial and final. So initial is the dark one. Final we haven't made yet. That's going to be in that flask, the volumetric flask is called. So this is going to be the 2s, the final. So I know everything over here. I know what I want. 250 here, 0.5 there. I have 12 here. What are we solving for?
V1.
V1. Let me erase this and rewrite it. Okay? So M1 is going to be 12. V1, we don't know, or X. M2, 0.5. V2, 250. Okay, 250 milliliters, molarity. So, while I go get, I know I'm going to need some things here. Grab a calculator if you need it. I don't really want you using your phone. Just set that up in your notes, solve for V1, give me an answer with units. Wait a second, let's make this more fun. Let's throw sig figs in.
Not sig fig.
Let's throw sig figs in. So let's go 12.0 is the molarity. Let's go 0.50 molarity, and then 250.0 milliliters. There you go. Set it up, solve for V1. Give me a unit and round to the proper number of sig figs. Getting out all the fancy glasswork here. Watso, set it up for me. Show your work, right? So how do I show my work? Molarity. Tell me what you wrote on your paper. You have something written down, right?
Yeah.
Okay, tell me. 12.0.
Yeah.
Hey, up here.
And then just like, I don't know, I'm like multiplying.
You're multiplying, I like that.
Yeah. By question mark.
Yep. I'll put an X or V1. Yep.
And equals 0.5 times 250.
There you go. That's what you need to show for your work, right? Fill in the equation. So M1 V1 equals M2 V2. What is this equation all about? The ratio of molarity to volume of the first solution. That ratio needs to be equal to this ratio. All right, now I know this isn't a ratio like division, right? So I guess I'm not using the right word, but we can say the proportions here. But these two multiplied should equal these two multiplied. All right, so you multiply these two, then divide by 12, right? So multiply and divide by 12. X equals 10 milliliters. But wait a second. I need sig figs.
That is it.
No, that only has one sig fig.
Oh.
Yeah. So 3 here, 2 here, 4 there. So it's got to be 10 with a decimal point at the end. I should have added a decimal here because you're not going to have to do that on the regions, but that is how it would look. So that's 1, 2 sig figs. In reality, they would probably do that. So then how would your answer change?
0.0.
10.0, right? That would be a more realistic. I kind of just did that in my head. I didn't think about it. Okay. Okay. So now, unfortunately, this isn't going to look a whole lot lighter, but here's how we would do this. So I take this thing, it's called a volumetric pipette or graduated pipette.
Alrighty.
Put this in here. Maybe. Or not. I don't really want to put this through my finger. That would be an unfortunate event. Okay. Safety first. Olivia. All right. Okay, this thing's cool. So I'm going to pull up 10 milliliters. Okay. Now I put it in here. See, this is the fancy stuff that you can use when you take AP Chem or if you're a chemistry teacher. Instead of graduated cylinders, which are just a pain. Okay. All right. So now that's super stain power, so. Just got some on my hand. That's cool. All right. Stain my finger, being on there for like 10 seconds. All right. So now what I would do is I would add distilled water. I'm not going to because that's a waste of distilled water, but I'll just go over to the tap or whatever, and I'm going to fill it up to this line, and then I'm going to put this top on it. So that's how you make a dilution. Bear with me. So you see the final result. So again, we would just fill it up to the line. Now we would use distilled water and be very careful about it, but I'm not going to do that.
This is street chemistry.
Alright. So it's still very dark, but you would invert it a couple times, and that's how you would make a dilution. Okay? So it's still very dark because this stuff is pretty potent, but it's a little bit lighter. Do you agree a little bit?
Yeah.
Yeah. Okay? So that's how you would make a dilution. So this is way, 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 way less concentrated, actually. So going from 12 to 0.5, and that's how you do it. So then I would just pour this out for whatever we needed. So that's how you make a dilution. You need to understand the concept of how to use that equation. M1V1 equals M2V2. Do me a favor. What calculation are you doing when you multiply volume by molarity?
No.
Let's look at units. What's the unit on molarity? Capital M, but give me more specifics. Moles per liter. Okay? So molarity equals moles per liter. That's the molarity formula. So the units here are moles per liter. If I multiply this by liters, what cancels out?
Liters.
Liters. What's left?
Moles.
Moles. So when you're doing M1V1 equals M2V2, what you're really doing is moles equals moles. That's what you're doing. And that's why that equation makes sense. If you don't understand that, that's fine. It really is. But that's how you do a dilution problem, okay? I'm going to write one on the board, copy it in your notes. I want you to finish it for homework. We're running out of time here. All right, so I'm going to give you a dilution problem, and you're basically going to explain exactly what I just did in front of you. Okay, so I'm going to give you a question, and I want you to answer it for homework. That's all you have is one problem. Don't worry, I'll make up for it the rest of the week. Here we go. So, how many milliliters of water are needed to dilute a stock solution of 18 molar HNO3, parentheses, you have 25 milliliters of it. How many milliliters of water are needed to dilute a stock solution of 18 molar HNO3, you have 25 milliliters, to a, let's see, where's my 2 molar HNO3 solution with a volume of 250 milliliters. All right, and then when I call on somebody randomly tomorrow, be prepared to explain how to make it, okay? Just like I did here. All right, so how many milliliters of water are needed to dilute a stock solution? That's your starting solution, 18, 25. That's like the dark stuff there. 2 and 250 is what you want. That's like this. That's what you want. Now, just real quick here. How do you figure this out? Let's use this example. How much of the original solution, so eyes up here, you have time to write that. How much of this did I use? 10. I sucked up 10 milliliters in here, put it in here. What's the final volume here? Says it right on, 250. So if I took 10 milliliters of the original stock solution and I put it in here, you saw it in the bottom before I put water in. How much water did I add? 240. That's how you answer this question. You're going to have to first figure out how much of the original you need by doing the M1V1 equals M2V2, just like we did, and then figure out, okay, if the total volume is 250, you just have to subtract how much of the original you used. So just what I did. I try to do it to show you because this is really kind of random, something you've never seen or done, so it's hard to visualize or understand. So that's why I literally make one so you can see it. All right. So tomorrow we're starting a new unit on kinetics and equilibrium. You will have homework the rest of the week, so I'll probably do Monday too. So Wednesday, Thursday, Friday. So we will make up for not having homework 2 nights in a row. And that's it. The bells aren't working, right? So you can pack up and get out of here. I don't want to see you again until tomorrow. Or actually, I'm after school. If anybody needs anything, I'm after school. Mike, when you finished in that quiz?
Are you after tomorrow?
No.
You have to do an outro.